Hello, this is a rather long four-part module on this technique which I call PCA for a regression. So don't mix it up with a PCA regression. There's a separate technique called PCA regression. I'll mention it. But here I'm using PCA for regression in two different ways. Our agenda is that first we're going to look at orthogonal regression as an alternative to OLS. That will be the first approach we will try or we will consider. We will see where it's applicable when we think that the relationship between variables is equal, not like dependent-independent type of thing in ordinary least squares regression. Then we'll talk about random regressors, where in such a case sometimes orthogonal regressions are prescribed, or type 2 regressions, and I'll say why I somewhat disagree with this prescription. Then we will touch on an important topic of a regression model matching its data generating process. And at the very end, in part 4, we'll look at step-by-step solution of a fun problem, which we will discuss in the very beginning of the video. So why don't we start now? What is OLS? So in a nutshell, what OLS does is minimizes the sum of squares. That's why it's called least squares, ordinary least squares. Squares of what? Squares of residual. So in a typical model, very simple representation of it I'm showing on screen, you have a dependent variable, y, and you have here I'm showing y, and then there's one independent variable. In this case I'm just using one for sort of demonstration purposes. Your model is intercept plus the slope on multiplied by the regressor or independent variable, and you see how I call the variables independent and dependent, so they're not in equal relationship, if you wish. We measure the dependent variable with some error which is not observed. We don't know this error. We can estimate this error, and how do we do that? Well, we pick coefficients beta 0 and beta 1, some set of coefficients, plug them into the model, and look at the difference between observed and predicted. So the quantity in on the right side here in the parentheses, this is predicted value, as we know. So the difference between predicted and observed would be a residual, which is an estimate of an error. Residual is, we can say it's observed, right? We can measure it. The error we cannot. We can only see the dependent variable where the error is baked inside. But we don't know what is it because we don't know the parameters. Now, how do we find parameters? Well, we minimize the sum of least squares, and that's basically what OLS is. And there's a lot of obviously advanced math around regression technique, but that's how it's been developed, right? Historically, we get the least, we get the squares, and then we find the minimum by trying different parameters. So what I'm showing in the plots here down, this is from one of the books which I'm referring to later, Numerical Ecology, because yeah, we'll see why. So what least squares minimizes is, as you've noticed, it minimizes the deviations of the predicted versus the observed, and predicted is represented by the solid line on this figure 10.6a. So the solid line is what is predicted, and dots are observations. So if we interpret, when we interpret the OLS, we should understand that we are minimizing the deviations which are depicted by these solid lines. These lines go from the observed data to the line, and notice that the distances which we are minimizing deviations are not perpendicular to the line. They're vertical because we are minimizing the deviations along the y-axis, dependent variable. So that is that's an OLS approach when we are regressing y on x. But what if we regress x on y? Well, then you will get the dotted line. And the dotted line, you see, we are minimizing, again, deviations from the line, which is predicted, to observed. But this time, the deviations are measured on a horizontal axis. And because we're minimizing different things, we have different lines. We find the optimal line, and it's different when we are minimizing when we're coming up with the regression y on x and x and y. You have to understand why, right? Because we are minimizing different quantities, different deviations. That's why we get different lines. Now, before we go into the detail of what I'm going to talk about today, I'll just say that there is a different way, there is a different quantity yet to minimize again. So imagine there was this line, and we'll call it major axis line. It will be principal component number 1. But when we found this line, what we did was we minimized the deviations, the distances from these observations to the line, right? Not horizontal or vertical deviations, but the perpendicular lines, right? So the perpendicular line is the shortest distance from the observed point or any point to a line. So in this regard, you see we are treating x and y equal, and that's what I meant by equal in the beginning of this module, right? The x and y are entering the relationship on equal terms. So y is not independent or dependent, or x is not dependent or independent. They're both going into this regression as equals, and that's why we're minimizing this distance. You can immediately see that there could be issues, right? So for instance, if y and x's are measured in different units, that could be an issue, right? Let's say one is kilogram, another one in dollars. How do you really minimize? Because this distance purely geometrically assumes that it's a Cartesian distance, assumes that probably the units are about the same, or the same units of measure, right? Dollars, or kilograms, and so on. It's kind of hard logically to see the distance when your x and y are different units of measure, but that's let's not talk about it at the moment, right? So we'll just say that there is a different regression line which we could find by minimizing the distances to the line, right? Not along the axis, but just on the plane geometrically, right? And that is orthogonal regression. It has many different names besides orthogonal and total least squares. So we are going to talk about the application of orthogonal regression as an alternative to OLS on an example. So we're going to look at this example. You can find it on Stack Exchange website, statistical what is it called, statistical site of Stack Exchange. I give you the link. You can follow and find all the discussion there. But original poster asked the following question. He said the common sense line of the best fit would appear be an almost vertical line straight through the center of the points, edited by hand in red, right, on this picture. However, the linear trend line, as decided by Excel, is diagonal black line. Why does OLS seem to be broken here? So my original poster was wondering why Excel is not finding this common sense line, right? And it's an interesting question, right? It's like a visual. You would say this red line is probably a better fit, yet Excel is doing something else. So it might be, you might think that it's just a pure maybe visual thing, that maybe it's just a matter of scale. Maybe we can change something there and so on. But I think the problem there was not it. The problem was that the variables in horizontal and vertical axis, they were entering the regression on equal terms, while the regression assumes that one of them is a function of another, right? There's independent and dependent. And I think that's why the regression was producing strange result, while if you treated the variables as equal, then maybe you would have gotten a better result. And we can get a hint of it from the further update to the question, right? So the question was posted originally, and then there were some updates. So one of the updates says the following: the data represent a paraglider climbing in a thermal whilst drifting with the wind. The final objective is to investigate how wind strength and direction varies with height. Wow, that's now that is interesting, right? So the x and y's are what? They are latitude and longitude. So you're moving in the wind. Paraglider is if you have seen, it's a person which glides basically on a kite, right? There's a big kite, I guess, and they're gliding in the air like a bird. That's the best analogy I can get, right? And thermal is the convection. It's like a stream in the air of, let's say, warm air, which is going upwards, let's say, right? And that's how actually birds also soar, and people. And there's one paper which I'm citing in this module, which I encourage you to look at, about comparing birds and I guess people paragliders. Okay, so right, so what we see here is this paraglider. He has this spiral motion, right? So let's take a look at it like this, right? So I forgot which one of each paraglider and which one of is a bird, right? And there's a link to the paper which compares them. But you see the spiral movement, right? So the paraglider, or maybe a bird, is making circles, and thermal is moving them, let's say, upwards. And there's a wind, and then wind can move them to some other direction. And clearly here, the latitude and longitude cannot be independent dependent. It's not like your latitude is defining your longitude. That's not the case, right? So it's your spiral movement, wind, and thermal, some other factors. They are defining your latitude and longitude. And if anything, latitude and longitude are probably on equal terms, and that's why I'm going to say that, well, maybe this type of major axis regression, maybe major axis regression should work. And on this plot, you see that it does work. So this is a plot which where sorry, is this? No, that's from the question. I'll show you the plot generated by where is it? Okay, here's the plot, right, which is generated by the orthogonal regression, where both latitude and longitude are both variables enter as equals. And let's discuss it in a little more detail in part 2.